Ever think of space races? Not the old school ones with rockets and moon landings.
Yeah.
I'm talking a brand new kind of space race. One where the battleground is inside computers.
Ooh, yeah.
A race to build the most powerful computer imaginable, one that runs on the absolutely mind-boggling laws of quantum physics.
A proper quantum Cold War, right?
Spot on. And get this, the prize isn't just bragging rights or planting a flag on some distant planet.
No, much bigger than that.
We're talking about potentially cracking every digital secret, building AI so smart it makes our current tech look like toys, and basically controlling the flow of information on a global scale.
Seriously high stakes.
No kidding. So the million-dollar question we're digging into today is, who's actually winning this intense global competition for quantum dominance?
It's where the world of cutting-edge science slams right into global power plays and, of course, mountains of cash.
Welcome back to Decoding Quantum Computing on The Curious Decoder. This is Season 1, Episode 6. We're calling this one The Race for Quantum Dominance, Who's Leading?
That's right, and as always, we're using the sources you sent us as our roadmap.
You guys really piled on the reading material this time, but that just means we've got a lot to unpack in this deep dive.
We want to cut through all the hype and see who's really ahead in this race that could totally change the technological landscape.
Now, in previous deep dives, we've chatted a bit about the fundamentals of quantum computing, but today we're zeroing in on the competition itself. We've got some fascinating articles to guide us, like The Race for Quantum Dominance, Who's Leading? And The Quantum Cold War, Inside the Secretive Battle to Build the World's First True Quantum Computer.
They really set the scene, those articles.
So our mission today is to trace the roots of this quantum quest, to pinpoint the big players. Are we talking about nations pouring billions into research, tech giants making huge bets, or those nimble startups trying to disrupt everything?
All of the above, actually.
We'll also be dissecting the different technical paths they're taking and the global economic forces that are fueling this whole shebang.
It's a complex landscape, that's for sure.
But let's be real. You're probably wondering who's going to come out on top in this field that could rewrite the rulebook on tech.
Absolutely. And we're here to unravel all the complicated bits, make sense of the jargon, and try to answer that very question.
So where did this whole quantum computing race actually spring from?
Well, it might sound like something straight out of a sci-fi movie, but this race has a real backstory. The seeds were actually planted way back in the early 20th century.
Really? That far back?
Yep, with the birth of quantum mechanics itself. Think of it as the wild, weird world of how atoms and particles actually behave.
I vaguely remember that from school, but it always made my head spin.
It's definitely not intuitive. But think about pioneers like Richard Feynman. He was a brilliant physicist.
Okay, I've heard the name.
Well, back in 1980, Feynman made this really crucial point. He said regular computers, the ones we use every day, just aren't up to the task of accurately simulating quantum systems. He argued that to properly grapple with the complexity of the quantum world, you'd need a computer that itself operates on quantum principles. A quantum computer.
That's a pretty radical idea.
It was, and it took a while for it to really catch on. Then, in 1985, David Deutsch formalized the concept of a universal quantum computer. Imagine a machine that could potentially leave classical computers in the dust for certain types of problems, like cracking those really hard mathematical codes.
So for quite a while, it was all just theory, right? Just clever folks kicking around ideas.
Pretty much. For many years, these were largely concepts confined to the world of theoretical physics, the domain of equations on blackboards rather than actual machines.
But eventually, things started to shift, didn't they?
Exactly. In the late 1990s and early 2000s, the real world started catching up to those theoretical ideas. Experimental physicists began actually building rudimentary quantum devices in their labs, manipulating individual atoms or photons, trying to get them to perform basic calculations.
So, like the very first baby steps of quantum computing.
You could say that, but then in 1994, a major turning point came along. Peter Shor's algorithm.
Ah, yes, Shor's algorithm. If I remember correctly, that's the one that sent a shiver down the spines of anyone who works in cryptography, right?
That's the one. Shor's algorithm showed that a quantum computer could, at least in theory, factor large numbers exponentially faster than any known method using classical computers.
And why is that such a big deal?
Well, our entire online security infrastructure, the way we protect our data and financial transactions, relies on the fact that it's extremely difficult for classical computers to factor those massive numbers. It would take them years, even centuries, to break the codes.
So our digital security is basically built on the limitations of current computers.
In a way, yes. But Shor's algorithm showed that a quantum computer could potentially bypass those limitations.
That must have set off some alarm bells.
It did, and that's when the initial scientific curiosity surrounding quantum computing really started to morph into something bigger. Governments, research institutions, and eventually big businesses started to wake up to the potential and the risks of this emerging technology. The race was on, even if it was still in its early stages.
And then things really accelerated in the 2010s, right?
Absolutely. The 2010s were a watershed moment. Companies with serious resources like IBM and Google started pouring huge amounts of money into quantum hardware research. Governments around the world launched national quantum initiatives, realizing that this technology could have significant strategic implications.
It sounds like people were starting to grasp the enormity of what quantum computing could achieve.
It was a real turning point. And then, of course, there was Google's 2019 announcement that sent shockwaves through the tech world, their claim of achieving quantum supremacy.
All right, let's break down that quantum supremacy claim because it certainly grabbed a lot of headlines.
Well, Google claimed that their Sycamore processor, which used 53 superconducting qubits, had performed a specific task in about 200 seconds that would have taken the most powerful supercomputer at the time around 10,000 years to complete.
Wow, 200 seconds versus 10,000 years. That's a pretty stark difference.
It was a bold statement, and there was some debate about whether Google's chosen task was truly representative and about the estimated time for a classical computer.
So some folks were skeptical.
There were definitely some dissenting voices, and IBM, another major player in the quantum field, put forward their own analysis suggesting that a classical supercomputer could have performed the same task in a much shorter time frame, but still considerably longer than Google's Sycamore.
It sounds like there's still some work to do in terms of how we measure and compare quantum versus classical computing power.
Absolutely. But regardless of the specifics, Google's announcement was a major milestone. It showed that quantum computers were no longer just a theoretical possibility, but were starting to perform tasks that were simply out of reach for even the most powerful classical computers.
It was a real signal that the quantum era was dawning. So we've laid out the historical context. Now let's get into the nitty-gritty of what actually makes quantum computers so special. It all comes down to the qubit, right?
You got it. The qubit is the fundamental building block of a quantum computer. Like the bit is for classical computers.
Okay, so bits and qubits, got it.
Yeah.
But what makes them different?
Well, a bit can be either a 0 or a 1. That's how classical computers store and process information.
Right, like an on or off switch.
Exactly. But a qubit, thanks to the magic of quantum mechanics, can exist in a state called superposition.
Now, you're going to have to explain that one because superposition always makes my brain hurt a little.
I hear you. It's one of those concepts that challenges our everyday intuition. Imagine a coin spinning in the air.
Okay, got it.
Before it lands, it's not heads or tails, it's both possibilities at the same time.
Right.
That's kind of what superposition is like. A qubit can be in a combination of 0 and 1 simultaneously until it's measured.
So it's not just one or the other, it's both. That's kind of blowing my mind.
It's definitely a bit trippy. But the key takeaway here is that this superposition allows a quantum computer to explore a vast number of possibilities all at once, unlike a classical computer, which has to plod through them one by one.
Okay, so a qubit is like a multitasking ninja, able to juggle many possibilities simultaneously.
A very apt analogy, but it gets even weirder because then we have to factor in entanglement.
Ah, entanglement. Another one of those quantum terms that makes me feel like I need a physics degree.
It's definitely a head-scratcher, but it's also one of the most powerful features of quantum mechanics. When two or more qubits become entangled, they're linked in a way that even Einstein called spooky action at a distance.
Spooky action at a distance. That sounds ominous.
It's not ominous, but it is mind-bending. Essentially, the state of one entangled qubit instantly affects the state of the other, no matter how far apart they are. It's like having two of those spinning coins, and when one lands on heads, the other instantly flips to tails, even if they're miles apart.
So they're connected in this invisible, instantaneous way.
Exactly. And that interconnectedness allows quantum computers to perform computations in a way that's fundamentally different from classical computers.
Okay, so superposition lets them explore tons of possibilities simultaneously, and entanglement lets them work together in a coordinated way. What does that actually mean in terms of raw computing power?
It means that quantum computers have the potential to absolutely smash classical computers when it comes to solving certain types of problems. We're talking about tasks that would take even the most powerful supercomputers today millions of years to complete, but a quantum computer could potentially do them in hours or even minutes.
Like what kind of tasks? Give us some examples.
Imagine being able to design completely new materials from scratch by simulating the behavior of atoms and molecules at an incredibly detailed level. That could revolutionize everything from batteries and solar cells to new drugs and therapies.
That would be huge for medicine and energy.
Absolutely. Another area where quantum computers could shine is optimization. Think about optimizing incredibly complex systems like global logistics networks, financial markets, or traffic flow in a megacity. A quantum computer could potentially find solutions that are far more efficient than anything we can achieve with classical computers.
So it's not just about speed, it's about finding better solutions.
Precisely. And then, of course, there's the whole field of cryptography that we talked about earlier. Quantum computers could potentially break the encryption that protects our online data, which is why there's a huge push to develop new quantum-resistant encryption methods.
It sounds like quantum computing could touch just about every aspect of our lives.
It really does have that potential. But it's important to remember that quantum computing is still in its early stages, and there are some significant challenges that need to be overcome before we see these world-changing applications become a reality.
You're about to tell me it's not all sunshine and roses, right? There must be some serious downsides to these quantum wonders.
You're absolutely right. One of the biggest hurdles in this race for quantum dominance is that qubits are incredibly sensitive.
Oh, right. I remember you mentioning that.
Any tiny bit of noise or interference from the environment can cause them to lose their delicate quantum state. It's like trying to balance a spinning plate on a stick in the middle of a hurricane.
And that's what you call decoherence, right?
Exactly. Decoherence is the enemy of quantum computing because it causes errors, and those errors can quickly snowball and make the results of a quantum computation completely unreliable.
So it's not just about building a quantum computer. It's about keeping it stable and protected.
It's like building a Formula One car that can go at incredible speeds, but also has the tendency to fall apart if it hits a bump in the road.
Okay, that's a vivid image.
Yeah.
So decoherence is a major challenge. What else?
Another big hurdle is that current quantum computers are still prone to making mistakes in their calculations, even without decoherence. And to make things even more difficult, many of the leading quantum computing technologies require extremely cold temperatures, close to absolute zero, to function properly.
Colder than our space.
You got it. That means building and maintaining these systems is incredibly complex and expensive. So the race isn't just about cramming as many qubits onto a chip as possible. It's about finding ways to make those qubits stable, to reduce errors, and to control them with a level of precision that's never been achieved before.
So it's not just a numbers game. It's about quality as much as quantity.
It's a multifaceted challenge that's pushing the boundaries of physics, engineering, and computer science.
Well, with all those challenges, it's pretty impressive that we've made it this far. So who are the main players in this quantum game?
It's a fascinating mix of established tech giants with their deep pockets and ambitious startups looking to disrupt the field. On the big company side, you've got the usual suspects: Google, IBM, and Microsoft, all investing heavily in quantum research.
It wouldn't be a tech race without them, would it? So let's start with Google, the ones who made that big quantum supremacy splash. What's their overall strategy?
Well, as we discussed, Google's quantum team has been focusing on superconducting qubits. They've shown a willingness to push the limits of qubit count with their Sycamore processor. But they're not just throwing qubits at the problem, they're also putting a lot of effort into improving coherence times, trying to make those delicate qubits last longer before decoherence sets in.
So making them more robust.
Exactly. And they're clearly aiming to leverage their strengths in areas like artificial intelligence and machine learning, where quantum computers could offer a significant advantage.
So Google is going for a combination of raw power and targeted applications.
It seems that way. They're betting big on near-term gains with superconducting qubits, hoping to find practical uses for quantum computers sooner rather than later.
And what about IBM? They've been in the computing game for decades. What's their approach?
IBM has been a quantum pioneer for sure. They've taken a very open and collaborative approach with their IBM Quantum Experience, which is a cloud-based platform that allows researchers and developers from around the world to experiment with their quantum computers.
That's pretty generous of them.
It's been a very smart move because it's allowed them to build a strong ecosystem around their technology. They've also been steadily increasing their qubit counts, with their 127-qubit Eagle processor being a significant milestone. But they're not just chasing big numbers. IBM is also placing a heavy emphasis on developing error correction techniques and building hybrid systems that combine the power of quantum computers with the reliability of classical computers.
So they're thinking about the long game, making sure those quantum computers are actually useful and reliable.
Absolutely. Their roadmap aims for fault-tolerant quantum computers by the 2030s, which is a pretty ambitious goal, but they're making steady progress.
So we've got Google going for speed and near-term applications, and IBM focusing on accessibility and long-term reliability. What about Microsoft? They're usually right in the mix when it comes to major tech advancements.
Microsoft is certainly in the race, but they've taken a slightly different path. They're investing heavily in the development of topological qubits, which, if they can get them to work, could be a real game changer.
Okay, I'm intrigued. What are topological qubits and why are they so special?
Topological qubits are based on some very complex and mind-bending physics. The theory is that they're inherently more resistant to decoherence and errors than other types of qubits.
That sounds like a massive advantage.
It would be huge, but there's a catch. Topological qubits are still very much in the experimental stage. Microsoft hasn't actually built a working topological qubit yet, at least not publicly.
So it's a high-risk, high-reward strategy.
Exactly. They're betting on a technology that could potentially leapfrog the competition, but it's a long shot at this point. In the meantime, they're also building a comprehensive software ecosystem, including their own quantum programming language called Jiuzhang, because they recognize that having the right tools to program these machines will be just as important as the hardware itself.
So they're hedging their bets, investing in both a potentially revolutionary hardware approach and the software needed to make it work.
Precisely. They're playing a long game, and it'll be fascinating to see if their bet on topological qubits pays off.
So we've got the big three tech giants, each with their own distinct approach. But what about the startups? Are they just trying to keep up, or are they bringing something new to the table?
The startup scene in quantum computing is incredibly vibrant, full of new ideas and a real sense of urgency. You've got companies like Rigetti Computing, which, like Google and IBM, is working with superconducting qubits, but they're focusing on a more modular and hybrid approach.
Modular and hybrid, what does that mean in the quantum world?
Well, modular means they're designing their systems in a way that allows them to be scaled up more easily by connecting smaller units together.
Like building a quantum computer out of Lego bricks.
Kind of like that. And hybrid means they're not just focused on building purely quantum computers. They're also exploring ways to integrate quantum processors with classical computers, creating systems that can leverage the strengths of both.
So they're trying to find practical solutions for specific problems rather than building the ultimate quantum machine.
It seems that way. They're targeting areas like optimization and material science, where quantum computers could offer a significant advantage even in their current, less than perfect state.
Makes sense. And then we have IonQ. They've been getting a lot of attention lately. What's their angle?
IonQ is taking a completely different technological path, focusing on trapped ion qubits. As we discussed earlier, trapped ions have some inherent advantages when it comes to stability and accuracy. They tend to have longer coherence times and higher gate fidelity, meaning they make fewer errors in their calculations.
So they're more reliable.
Potentially, yes. And they've been making some impressive partnerships with big players like Amazon and Microsoft, which gives them access to resources and expertise that could help them scale up their technology.
And those partnerships could also open doors to new markets and customers.
Absolutely. It's a smart strategy.
Are there any other startups we should keep an eye on?
Definitely. There's Xanadu, which is working on photonic qubits using particles of light for quantum computation. This approach has the potential to work at room temperature, which would be a huge simplification compared to the ultra-low temperatures required for superconducting and trapped ion qubits.
That would certainly make things easier.
And photons are already used extensively in fiber optic networks, so there's existing infrastructure that could potentially be adapted for quantum communication and networking.
So they could have a leg up when it comes to connecting quantum computers together.
That's one of the potential advantages. And then there's D-Wave, which is taking a different approach with a technique called quantum annealing. It's not a general-purpose quantum computer, but it's particularly well-suited for solving optimization problems. And they already have real-world customers, like Volkswagen, who are using their technology to optimize traffic flow in cities.
So even in these early stages, quantum computing is starting to have a real-world impact.
It is, and that's just the beginning. The startup scene is constantly evolving, and it's likely that we'll see even more innovative companies emerge in the coming years.
It's an incredibly dynamic field. Okay, we've talked about the big companies and the startups, but it seems like there are a lot of different ways to actually build a quantum computer. Can we dive into the pros and cons of those different approaches?
Of course. Let's start with superconducting qubits, which, as we've mentioned, are favored by Google, IBM, and Rigetti, among others. The big advantage of superconducting qubits is speed. They can perform operations very quickly.
So they're the speed demons of the quantum world.
In a way, yes. And because they're based on superconducting circuits, which are already used in various technologies, they're somewhat compatible with existing chip-making processes. That can make it easier to mass produce them in the future.
So there's potential for scalability.
Potentially, yes. However, there are some significant downsides. As we've discussed, they need to be kept at extremely low temperatures, just a fraction of a degree above absolute zero.
Brr, that's chilly.
It is, and that requires complex and expensive cryogenic systems. Plus, superconducting qubits are very susceptible to decoherence, meaning those pesky errors can creep in quite easily.
So they're fast, but they're also a bit fragile. What about trapped ion qubits? How do they compare?
Trapped ions have the advantage of being naturally more stable. Because they're individual atoms suspended in a vacuum, they're much less affected by external noise, which means they have longer coherence times and higher gate fidelity than superconducting qubits.
So they're the steady and reliable workhorses.
You could say that. However, the downside is that they tend to be slower than superconducting qubits. Manipulating those ions with lasers is a more delicate and time-consuming process, and scaling trapped ion systems up to large numbers of qubits presents some significant engineering challenges.
So there's a trade-off between speed and stability.
It seems that way with current technology. And then we have the photonic approach, using particles of light. Photonic qubits have the potential to operate at room temperature, which would be a major advantage in terms of cost and complexity.
No more ultra-cold fridges. That would be a game changer.
It would, but the challenge with photonic qubits is that they're more difficult to control and manipulate. Light doesn't like to stay put, and getting photons to interact in a way that's useful for computation is a tricky business.
So it's a promising approach, but there's still a lot of research to be done.
Absolutely. And there are other promising technologies on the horizon, like quantum dots and nitrogen vacancy centers and diamonds. Each of these approaches has its own set of strengths and weaknesses, and it's quite possible that the ultimate winner in this race for quantum dominance might not be a single technology, but rather a combination of different approaches, creating hybrid systems that leverage the best of each.
So it's not just about picking a lane and sticking with it.
It's more like a decathlon, where you need to be good at a variety of different things.
Now, looking beyond the technology itself, there are some pretty big geopolitical and economic forces at play here. This isn't just a friendly academic competition.
It's definitely not. Quantum computing has become a major focal point in the global race for technological supremacy. Governments around the world recognize the potential for this technology to shift the balance of power in areas like national security, economics, and scientific advancement.
It's like the space race of the 21st century.
A very apt comparison. The United States, through its National Quantum Initiative, is investing billions of dollars in quantum research. They're particularly concerned about falling behind China, which has its own ambitious quantum programs and has already made significant progress, particularly in the field of quantum communication.
I've heard about China's quantum satellite. That seems like a pretty big deal.
It is. They've been investing heavily in building a quantum communication network that would be virtually unhackable, which could have major implications for military and government communications.
So there's a real sense of urgency in the U.S. to stay ahead.
Absolutely. They see quantum computing as a crucial technology for maintaining their global leadership in the 21st century. But it's not just a two-horse race. The European Union, through its Quantum Flagship Initiative, is also investing significant resources in quantum research, as are countries like Japan, Canada, and Australia.
So it's a truly global competition.
It is, and the stakes are high. The potential military applications of quantum computing, like cracking current encryption methods or designing new weapon systems, are certainly driving a lot of the investment.
It sounds like we're on the cusp of a major technological revolution.
It does feel that way, and the economic implications are just as significant. Some analysts predict that quantum computing could add trillions of dollars to the global economy in the coming decades.
Trillions? That's almost unimaginable amount of money.
It is, but it reflects the potential for this technology to transform entire industries. We've already talked about some of the areas where quantum computing could have a major impact, like drug discovery, material science, and logistics. But the possibilities go far beyond that. Imagine quantum algorithms that can optimize financial markets, revolutionize artificial intelligence, or even help us understand the fundamental nature of the universe.
It's both exciting and a little bit terrifying to think about the possibilities.
It is, and it's important to have open and honest conversations about both the potential benefits and the potential risks of quantum computing.
Agreed. But with all this hype and investment, there must still be some major hurdles to overcome before we see these world-changing applications become a reality.
Absolutely. As we've discussed, error correction and decoherence are probably the biggest roadblocks right now. Qubits are incredibly fragile, and any little bit of noise from the environment can cause them to lose their quantum information.
Right. It's like trying to build a sandcastle on a windy beach.
It's a very apt analogy. And even with perfect qubits, errors can still creep in during the calculations themselves. So, to build truly reliable quantum computers, we need to develop incredibly robust error correction methods. One promising approach is called the surface code, which involves encoding a single logical qubit across a large number of physical qubits.
So you need lots of physical qubits to create one reliable logical qubit.
Exactly. And that brings us to another major challenge: scalability. Building quantum computers with millions of qubits, which is what we'll likely need for many of those world-changing applications, is a monumental engineering challenge.
It sounds like we're talking about pushing the boundaries of what's currently possible.
We are. Just think about the complexity of wiring up millions of qubits, keeping them at ultra-low temperatures, and controlling them with incredible precision. It's a daunting task.
So we need some major breakthroughs in both the science and the engineering.
We do, and that's why there's so much research and development happening right now. The race for quantum dominance is a marathon, not a sprint, and there are still many hurdles to overcome.
And how do we even know when we've actually reached quantum dominance? It's not like we can just run the same calculation on a classical computer and a quantum computer and see which one is faster.
It's not that simple, unfortunately. Evaluating the performance of quantum computers is a complex task because they work in a fundamentally different way than classical computers. We need to develop new benchmarks and metrics that can accurately capture their capabilities. The whole debate about Google's quantum supremacy claim highlighted this challenge.
Right. Because IBM argued that a classical supercomputer could still perform the same task, just not as quickly.
Exactly. It's still an open question how we define and measure quantum advantage, and that's a topic of active research and debate within the field.
So there's still a bit of a Wild West element to this race.
There is, and it's part of what makes it so exciting.
So looking ahead, what are some realistic expectations for the next few years? Are we all going to have quantum computers on our desks by next week?
Chuckles, probably not that soon. But the next decade is likely to see some significant milestones. Many experts predict that we'll have fault-tolerant quantum computers with hundreds or even thousands of qubits by 2030.
Okay, that's a bit more realistic.
And we're likely to see those hybrid quantum classical systems becoming more prevalent, where quantum processors are used for specific tasks that are well-suited to their capabilities.
So a gradual integration of quantum computing into existing systems.
Exactly. And it's important to remember that general-purpose, fully fault-tolerant quantum computers that can solve any problem are still likely decades away.
So it's a long-term game.
It is, and it's one that requires collaboration and open communication. We need to share knowledge and resources to accelerate progress. That's why initiatives like the Quantum Economic Development Consortium, QEDC, are so important. They bring together industry, academia, and government to work on common challenges and set standards for the field.
So it's not just about competition, it's also about cooperation.
Absolutely. And the open source movement is also playing a crucial role in democratizing access to quantum computing tools and resources. Platforms like IBM's Qiskit are allowing anyone with an internet connection to experiment with quantum algorithms and learn about this exciting technology.
It sounds like there's a real sense of community and shared purpose in the quantum world.
There is, and that's one of the things that makes it so inspiring.
Well, we've covered a lot of ground in this deep dive. For our listeners who've been following along, what are the key takeaways they should remember about this race for quantum dominance?
First, it's a global race with high stakes. Nations and companies around the world are investing heavily in quantum computing because they recognize its potential to transform everything from national security to the global economy.
So pay attention, folks. This is important stuff.
Second, there's no clear winner yet. We're seeing a diverse range of technological approaches, each with its own advantages and disadvantages. The ultimate solution might be a combination of different technologies, creating hybrid systems that leverage the best of each.
So it's a horse race with a lot of different horses, and it's still anyone's game.
Exactly. And third, while there has been incredible progress in recent years, there are still major challenges to overcome, particularly in the areas of error correction and scalability. Building truly reliable and powerful quantum computers is a monumental task that will require continued innovation and collaboration.
So it's a marathon, not a sprint.
Precisely. And the finish line is still a long way off, but the journey is fascinating and the potential rewards are enormous.
It's an exciting time to be following this field, that's for sure. Now, for our listeners who have joined us on this deep dive into the quantum world, here's a final thought to ponder. Given the immense potential of quantum computing to reshape everything from medicine to artificial intelligence, what do you think the world will look like when quantum computers become as ubiquitous as smartphones are today? What new possibilities will emerge? What new challenges will we face?
Those are great questions, and they really get to the heart of why this race for quantum dominance is so important.
It's not just about building faster computers. It's about shaping the future of technology and, ultimately, the future of humanity.
Well said. And that brings us to the end of our deep dive. Thank you for joining us on this exploration of the quantum world.
Decoding the universe, one mystery at a time.
Yeah.
And the race for quantum dominance is certainly one of the biggest mysteries we're currently trying to decode. We'll catch you next time.